Today, we're going to crack open a document from 50 years ago that, believe it or not, quietly designed the digital world we all live in.
I mean, really think about it for a second. When you log onto your computer, how does it know that these are your photos and those are your private emails and that your roommate shouldn't be able to see them? What's stopping it all from being a jumbled mess?
Well, believe it or not, the answer, the fundamental blueprint for your digital privacy, was hammered out in a research paper all the way back in 1974. Yeah, that's years before the first personal computer was even a thing.
So, let's get into it. The paper was by two guys, Jerome Salter and Michael Schroeder, and they saw the future coming. They realized that once you have multiple people using the same computer at the same time, you desperately need a system to control who gets to see and do what. They were thinking about things like airline reservation systems, but what they were actually doing was building the foundation for, well, everything. Your Google Docs, your company's network, all of it.
So, what was the big problem they were really trying to get their heads around? See, back in '74, computers were these enormous, wildly expensive mainframes. The whole point was to let a bunch of people share one powerful machine. But that's a huge problem, right? How do you stop one person from accidentally, or, not so accidentally, wiping out somebody else's work? How do you keep it from turning into a total free-for-all?
And their solution? It wasn't just some technical jargon. No, they came up with a whole philosophy for security, a set of 8 core design principles that are, frankly, still shocking in how relevant they are today.
Okay, let's zoom in on 3 of these principles because they are truly the bedrock of almost all modern digital security. First up is this idea of least privilege, and it is brilliant in its simplicity. Basically, it says, don't give any program or user more power than it absolutely needs to do its job. It's why your calculator app shouldn't be asking for access to your contacts, right? By limiting power, you contain the damage. If something goes wrong or gets hacked, the problem can't spread. Next, we have fail-safe defaults. This just means that the default answer to, can I access this, should always be no. You have to be explicitly given permission. Think about it. It's way safer to have a guest list of who's allowed in instead of a list of who's kicked out. That way, if you forget to add someone, the system fails safely by just keeping the door locked. And finally, this one's a big one, open design. They argued that your security shouldn't come from hiding how your system works. It should come from having an incredibly strong key, like a password. The thinking is, a truly strong lock should work even if everyone on the planet has the blueprint for it. This is why so much critical security software today is open source. Its strength comes from being constantly attacked and tested by experts in the open.
So, with these ground rules in place, the paper then gets into the nitty-gritty. It lays out 2 totally different, competing ways you could actually build the digital guards that enforce these rules. And this is where it gets really interesting.
The first model is pretty easy to picture. It's like having a bouncer at the door of every single file, and that bouncer has a very strict guest list.
The technical name for this is an access control list, or ACL, and it's just what it sounds like. Every file, every folder has a little list attached to it that says, okay, Sarah can read this, Dave can read and write, and absolutely nobody else can touch it.
And the process is exactly what you'd expect. You try to open something, the computer looks at that file's personal guest list. Is your name on it? Yep, cool, you're in. Nope, sorry, access denied. Simple, right? But then they proposed a completely different approach. It's less like a bouncer with a list and more like a concert where what matters is that you have a special, impossible-to-fake ticket. This is called a capability. And here, the whole idea is flipped. Instead of the file keeping track of who's allowed in, you, the user, hold the proof. It's like a digital key. If you have the key for that file, you can get in, period. The file doesn't need to know who you are. So here, you just show up with your digital ticket, the system glances at it, confirms it's the real deal, that it hasn't been forged, and lets you write in. It's much faster because there's no list to check. It's a simple yes or no based on what you're holding.
Okay, so you've got the bouncer's list versus the unforgeable ticket. And this is the core of it. Neither one is perfect. They both have some pretty serious pros and cons. It's a classic engineering trade-off.
The bouncer's list gives you amazing control. It's super easy to look at a file and see exactly who can access it. And if you want to kick someone out, you just erase their name from the list. Done. But it can be slow. The unforgivable ticket, on the other hand, is lightning fast, and it's easy to pass your ticket to someone else if you want to give them access. But that's also its huge weakness. Once you give a ticket to someone, how do you ever get it back? Revoking permission is a total nightmare.
So which one won? In this big battle of ideas, did the strict bouncer or the flexible ticket come out on top? Well, the truly brilliant answer is both. Today's computer systems, from the one on your desk to the one in your pocket, don't actually choose. They perform this clever sleight of hand where they use the strengths of both models.
And was just mind-blowing is that Salzer and Schroeder predicted this exact thing would happen way back in 1974. At the surface, what you and I see are the guest lists, when you right-click a folder and set permissions. But under the hood, to make things run fast, the system is handing out temporary high-speed tickets to get things done. It's the best of both worlds.
This design, this hybrid model, has served us incredibly well for half a century. It's the foundation of everything. But as we start building these new worlds, with AI agents acting on our behalf, with decentralized networks, with the metaverse, you have to ask the question, will this 50-year-old blueprint still hold up, or are we going to need a completely new one for the next 50 years?